We go. Okay. Let's get started. Okay, welcome to TCC 2022, everybody. My name is David Cash. I am your general chair. I'm a professor here at the University of Chicago, which is where you are today. I'll start with the most important thing. The Wi-Fi password is study hotels. Okay, with a capital S and a capital H. It's written on the signs at the back tables and at various places. Use the meetings and events one. That one's stronger down here. I'll start with the second most important thing, which is where are the bathrooms? We have a small bathroom right outside next to the stairs. You could see with my fancy diagram here, if you just exit the lecture hall on the way to the stairs, you'll see the bathroom. There is a secret bathroom much further away that if you're frustrated with lines, you can go to. It involves going up the stairs, going past here. By the way, lunch is right up the stairs each day. You'll walk past this room with a bunch of round tables, going to the other side of the hotel down this hall, and then there's a bathroom in that corner of the hotel. Okay, so yes, take a picture. Wi-Fi and bathrooms. We're set to get to the less important stuff now. So welcome to Hyde Park, Chicago. You're on the south side of Chicago in the historic neighborhood of Hyde Park. This is what it looks like in the summer. It's a beautiful sort of residential neighborhood. I encourage you to explore it a little bit in your off time here. And you picked a great week to be here. The weather is not always like this in November in Chicago. It is often snowy by now. So we're quite lucky to be enjoying the weather this year. If you look in your bag, the backpack we handed out, I made a neighborhood guide to sort of encourage you to get out of the hotel a little bit and explore the neighborhood, especially since a lot of the things to do are not visible from the hotel. In general, you want to exit the hotel and cross this park that's in front of us called the Midway. So this way is north. I've circled the places where there tend to be restaurants. Around here is this really beautiful historic part of campus, the Gothic buildings and everything. And if you have a minute to go for a walk, it's really nice. If you want to go for a longer walk, I recommend sort of going through the neighborhood up here to this place called Promontory Point, which looks like this. You can get a view of the Loop. It's one of the most beautiful places in Chicago, especially this time of year. So next, so the conference program is online with all of the talks as you'd usually expect, coffee breaks and lunches. In the evenings, tonight is our free evening. We, at the last minute, added a business meeting today at 5 o'clock. So immediately after the last session in here, we're going to have a half hour to discuss sort of the future of TCC, how we might arrange and change the conference over time. If you have opinions or you want to hear opinions, please stay for that. On Tuesday, we're going to have a conference dinner in this room. Drinks will be served at 6:30 outside. The food will be served at 7. We do need to exit this room for an hour and a half tomorrow afternoon so they can put in tables and rearrange it for the dinner. And then Wednesday, we have a social event, which I will talk about on the next slide. And Thursday, we'll conclude, I believe, at 4 p.m. unless the program got changed. But of course, it is all online and also printed out in your bag. So Wednesday evening, I really hope all of you can come to a boat tour that we've arranged. So we will take buses from outside the hotel to downtown Chicago, and the buses depart at 5:30. So please try to get on those buses. It's kind of difficult if you miss it to sort of catch up and get on the boat. The boat tour itself will be from 6:30 to 8:30. This is my favorite sort of tourist activity to do in Chicago. There's going to be food and drinks, and for the initial part of it, some architecture commentary as we ride around this beautiful river that cuts through the center of Chicago. Weather permitting, we'll take the boat out into the lake and get a view of the city, and it should be a really nice time. Don't miss the boat. Obviously, if the boat leaves, you miss the whole thing. You can't get on late. And also, I've tried to arrange so that vegetarian and vegan food is available for everybody registered. The boat had some odd arrangement that the vegan food is only available if you go and ask them for it. So please only ask for the vegan food if you registered as your required vegan food when you register for the conference. Don't just pilfer the vegan food. Great. So other highlights of the conference include 2 invited speakers, Rahul Santanam, today at 11 o'clock, and Aaron Tromer Wednesday at 11 o'clock. Their talk titles and information are in the program. Encourage everybody to attend those. They're very generous with their time and effort to travel all the way here to give those talks. We also have a Test of Time award talk given by Jesper tomorrow at 4 o'clock. So we'll have this talk sort of to cap off the day. Then there'll be a break before the dinner. So this award has already been announced for their work from TCC 2011 with Ivan Damgaard, Sigurd Melgaard, and of course Jesper on perfectly secure oblivious RAM without random oracles. Okay. Finally, I want to stress close with two other things that I just want to mention before we move on to the talks. First is the IACR has adopted a code of conduct at all of its events. I encourage you to read this if you haven't. This is a screenshot from the conference website. Our statement basically says that everyone is entitled to be here without any sort of harassment or discrimination, and with full, respect. We're going to respect the dignity of every participant. If you see anything concerning at all, you're encouraged to intervene. You can contact me, or you can contact Shai, who's here, part of the ethics committee, or the other people here remotely listed there. And I want to close by saying I've attended conferences for a long time, almost 20 years. I never really thought about how much work goes into these conferences. Now I know. And it's not just me. It's a tremendous amount of work by volunteers, including Sandy Quarles, who's with UChicago CS, who you may have met on the way in. Who has done a tremendous amount of work with me for what feels like years, given all of the pandemic delays and everything getting started. But we also have 4 student volunteers who you'll meet. Alex, who's here, who will be putting the mic on you if you're speaking. Jesse, who will be running a mic to you if you ask a question. And JN and Sam, who will be doing various things involving registration and AV. So I think they deserve a round of applause while we get set up for the rest of the conference. Okay, and with that, we'll get started with our first technical session. That is on. Turn this off. Kay, is everything good to go?
Yes, it sounds great.
Okay, we have our speaker ready to go. We're just one more minute, and then Fermi's going to start the introduction.
Hi, everyone. My name is Fermi. I'll be chairing the first session on post-quantum cryptography. We have 4 fantastic talks coming up, and starting us off is Ethan Mook, who's going to tell us about post-quantum insecurity from LWE.
Okay, hello. My name is Ethan Mook. I'm going to be talking about getting post-quantum insecurity from LWE. This is joint work with Alex Lombardi, Willie Quash, and Daniel Wicks. The central question of this work is whether proving security under LWE always necessarily gives us post-quantum security. And it's been known for quite some time that the answer, at least for interactive protocols, is no. And there is extensive prior work showing that the security proofs for various different security properties you might want for an interactive protocol break down when you move to the post-quantum setting. And kind of the main issue here is with rewinding, which I'll get to in a little bit. But I also want to comment that this is not just a failure of the proof techniques. We actually have like explicit examples of things where there's some security property that holds classically, but not in a post-quantum setting. But we can ask the question, what about non-interactive primitives? Like many of the most fundamental primitives we consider in cryptography are primitives that are modeled as stateless functions where nothing about the functionality is really interactive. And so you could have this reasonable hope that since rewinding doesn't show up here, that security from LWE will necessarily imply post-quantum security. The main result of this paper is that this is not the case. And we give examples of some explicit yet contrived counterexamples for non-interactive primitives, these listed in red, like pseudorandom functions, max, signatures, CPA secure, symmetric key, and CCA public key secure encryption that are classically secure under LWE, but quantumly broken. The core technique, the core observation that we have is that many of these primitives, many of these non-interactive primitives actually have an interactive security game. And so therefore, you could see how rewinding could be an issue. And so like our kind of intuitive goal is that we're going to force the reduction to rewind the adversary somehow. And the main technique is that we're going to embed a so-called interactive proof of quantumness into the primitive that will catastrophically fail when the adversary is quantum. And so backing up a little bit, I just want to comment about why is this surprising and what does go wrong. So typically we we prove security by giving a black box reduction, and it doesn't seem, like on a superficial level, you might think that since this is a black box, it shouldn't matter whether the adversary is classical or quantum. However, there's like this fundamental mismatch in the interface the reduction gives when it is between a classical and the quantum setting. And so this comes up with rewinding. And kind of the idea is that a classical reduction, it's like a common technique, that a classical reduction may want to run the adversary many times, and it may revert to an earlier execution and restore the previous state before running it again. However, in the quantum setting, this doesn't work, because if the adversary, or if the reduction tries to rewind the adversary, the quantum adversary may make some measurement that collapses its quantum state and prevents any consistency between these different rewindings, causing the proof of security to fail. And indeed, this is something that can be explicitly realized, and this is introduced in the work of Brzezinski, Cristiano, Mahadev, Bezzerano, and Vidic, where they introduced this notion of interactive proofs of quantumness, where the setup here is that there's a prover and a verifier. And the verifier is purely classical, and they send classical messages back and forth. And the prover is trying to convince the verifier that he is quantum. And we want completeness, that a quantum prover can convince the verifier, but a classical prover cannot convince the verifier, but with negligible probability. And from a slightly different perspective, we can think of soundness as being a security property that holds in the classical setting, but completeness gives an explicit attack, an explicit quantum attack. And so we can kind of think of an interactive proof of quantumness as like a primitive where rewinding, or at least some notion of the reduction failing for quantum adversaries is inherent. And so any reduction will fail when you give it a quantum adversary. And the work of Brzezinski et al. Gives a 4-round interactive proof of quantumness from LWE. And so what we do with this interactive proof of quantumness is we given here is a specific example for signatures. We're just going to embed it into this protocol. And so for instance, the verification key will contain the first interactive proof of quantumness verifier message. And then kind of each signing query that the adversary sends in this the signing security game will be parsed as the next prover message in the IPQ. And the signing oracle responds with the next verifier message concatenated with some normal signature. And we continue this process until we reach the end. And at the end, the signing oracle will check if the IPQ verifier accepts. And then if it does, it says the signing, the signature of an accepting prover message is just the secret key. And so kind of the idea is that IPQ soundness implies that this doesn't affect classical security. We still have classical security, but completeness implies that there is an explicit quantum break. However, there's a problem here is that we've now introduced some state into the signing oracle because the IPQ is a stateful interactive protocol. And we want to fix this because normally we don't think of signatures as being stateful. And so our observation is that the IPQ from Brzezinski et al. Is public coin after the first verifier message. So it satisfies some notion of, it's hidden there, but resettable soundness. And so the idea is that we kind of hard code some randomness in the signing oracle, and all the verifier messages in the interactive proof of quantumness are just computed as a PRF of the message, and we interpret each message now as an entire partial transcript of an IPQ run. And then at the end, we can still just check if this entire transcript is satisfied and send the security or the secret key over as the signature. We also give a couple other results and like the kind of the main idea is that we give this like kind of way to compress the number of rounds and get an object like a protocol that has 3 rounds, like that takes only 3 rounds, but gives some quantum advantage by the end of it. And we use that to construct counterexamples for one-time versions of these same primitives that are quantumly broken in fewer queries, but we only get like one-time security because we've lost this notion of resettable soundness. I just want to close with a couple of open problems. Is you may have noticed at the beginning of the talk that we don't get a counterexample for CPA public key encryption. And kind of the idea is that our techniques fail because the final, like the condition of whether the adversary wins is publicly verifiable in the CPA security game, and our 3-round protocol doesn't allow this to work. And the second open problem is what about like truly non-interactive primitives? So for instance, one-way functions and PRGs, their security games don't have any interaction in them, and so therefore there's no real way to see how rewinding could have an effect. And like seemingly we would require some non-black box techniques because that's the only other place where we see that reductions fail going from classical to quantum. And the recent work of Yamakawa and Zandri shows that there are counterexamples for one-way functions in the random oracle model, but this is somehow fundamentally different. And so here's just a summary of everything I've talked about, but I think kind of the key takeaway here is that we just this work adds more evidence to the claim that reduction
The podium is muted.
Yes, we cannot hear you on Zoom. We still can't hear on Zoom. My apologies for interrupting.
Oh,
It
how
muted
did,
when you, I don't know.
how did that, what? Okay. Okay, so the question was whether there's like some positive notion that we can think of that, some way to tell whether a reduction is post-quantum, like say for sure that a reduction is like quantum compatible. And I think there are some notions that give at least like a limited class of reductions that we can tell are post-quantum compatible. I don't have them off the top of my head, but like in our work, we don't like explicitly give any of these positive results.
So maybe I'll ask a question. Could you say a little bit more about the barrier for CPA? Like, what is the big deal with public verifiability?
Yeah, so so the idea is that like to tell whether okay, so like there's the challenger in the CPA security game doesn't have like some secret state that it uses to determine whether the verifier has won or not. And so like it's really like two things. It's both the fact that the security game has very little interaction. Like the verifier just gets a public key, sends a challenge query, and then gets back the encrypted query, like one of the two. And so it's like this 3-round protocol, and so we need to use this 3-round construction that we have. However, that 3-round, like in the case of like whether the adversary has won or not can be verified simply with the public key. And it's true. This is true. Yeah. And so like and this is not something that our 3-round protocol is capable of achieving.
So maybe just a quick follow-up on that is I guess, are you saying that anytime you have a separation like this gives you also, like if you have a primitive whose security game, or if you have a primitive with an interactive security game and you have a quantum attack and a classical security proof, is that just an example of a proof of quantumness? And are you saying that maybe here you'd get a new proof of quantumness that we don't know, and that's sort of a barrier? Or is it just a barrier for your techniques? Sorry, just like, yeah, do separations imply proofs of quantumness?
Yeah, I think in some weak sense, yeah, at least. And yeah, and so like we only know how to get like these 4-round proof of quantumness. We don't know a lower level of interaction, and so the CPA security game is only 3 rounds, and just like the tricks that we use to get into like to handle 3-round things don't happen to work for CPA, and so it would imply a stronger proof of quantum.
Any other questions? I think we have another minute.
Is your feeling that there is a counterexample for CPA security, or could it be possible that every CPA secure encryption scheme from LWE is post-quantum secure?
I would find it somewhat surprising if every CPA, like if there wasn't a counterexample, I think, but yeah, that's really kind of just intuitive. I mean, yeah, that's really just not based on much.
Okay. Thanks.
Does using multi-challenge CPA make any difference? You get more rounds there, right?
I'm not super familiar with the security game there and like how it works. But I guess like conceivably, if just like if you have more rounds of interaction, like we actually only need just to embed this 4-round proof of quantumness, and so if you have at least 4 rounds of interaction, I think should be okay, but I don't know. Super.
Thanks.
All right, thank you. Let's thank the speaker again.
Hello. Yeah.
All right. So up next, we have Yushuan Huang, who will tell us about adaptive versus static multi-oracle algorithms and quantum security of a split key PRF.
Thanks for the introduction. This is joint work with Yale Dang and Serge Vier. First, I'm going to introduce the notion of adaptive and static multi-oracle algorithm. An oracle algorithm is an algorithm carrying a possibly randomized function for free. And here we are having an additional assumption that there's a fixed upper bound Q on the number of queries with oracles. We can extend this to the multi-oracle algorithm, where an algorithm can make query to multiple functions. And likewise, we have assumption on having a fixed upper bound for each respective number of queries to every oracles. Within those multi-oracle algorithms, we also consider a restricted class called static multi-oracle algorithm, which are those with predetermined querying order. So we consider both classical and quantum algorithm. In the quantum case, the query may be performed in superposition. In contrast, an adaptive algorithm can make a query, decide which oracle to query depending on its previous querying output. So why do we care about static algorithm? First, it is easier for analysis, and sometimes it gives better bound. But we stress also that in general, one cannot assume an algorithm is a static algorithm. So here are some situation cryptographic setting where multi-oracle algorithms are in presence. So our results consist of two parts. In the first part, we give a generic compiler transforming any adaptive algorithm, be it classical or quantum, to a static one, and with only a mild blow up on its query complexity. More concretely, if an adaptive algorithm makes Q1 to Qn respective queries with oracles, then after compilation, it makes n times Q1 to n times Qn respective queries only. With this, we can simplify existing results, but also enhance bounds. In the second part, we show the quantum security of a particularly efficient split key random function constructed by Gaikon, Huro, and Petrin in 2018, where the security is analyzed in the so-called quantum random oracle model. Consequently, an efficient CAM combiner is quantum secure. And since our analysis crucially relies on the compiler, it can also be regarded as the main application of our compiler. So moving on to the compiler. Our compiler works by running an interactive algorithm V between the adaptive algorithm A and the oracles by sort of rerouting the queries of A. Let's consider a naive compiler where when there are only two oracles, which basically just interleaving the queries to O1 and O2 for Q1 plus Q2 times. This naive compiled algorithm makes Q1 plus Q2 queries to both oracles, where Q1, Q2 are the queries to O1, O2 originally. But what if Q1 is Q2 squared? Then in this case, it makes roughly Q1 queries to both oracles, which are a lot bigger than Q2. This is an undesirable blow up on the query complexity because we actually want to have roughly Q1 queries to O1 and roughly Q2 queries to O2. We can put this situation into a more abstract formulation, namely the querying order after compilation, string S, 1, 2, 1, 2, 1, 2, etc. for Q1 plus Q2 times is a supersequence of every string S prime having the so-called characteristic Q1, Q2, where we are using the terminology that the string S prime having characteristic Q1, Q2 if every symbol sigma occurs in S prime for at most Q sigma times. The problem of naive construction is then the string S is now having characteristic Q1 plus Q2 for both symbols. And our goal is to find such a string S in, say, characteristic 2 times Q1 and 2 times Q2. looking at some example, when Q1, Q2 are 1 and 3, then we can choose this S as shown here. Indeed, it is having characteristic no more than 2 times Q1 and 2 times Q2. And indeed, it contains every such string S prime as a subsequence. We also know that the string S prime may be non-consecutively contained in string S as a subsequence. Yeah. More generally, we can show that there is a string S having characteristic n times Q1 to n times Qn, such that every string S prime having this characteristic Q1 to Qn is a subsequence of S. And furthermore, this string S is efficient to compute. So how do we construct this S? The idea is quite simple. We distribute the symbol, every symbol sigma evenly within the interval 0 to n and collect them from left to right. For this symbol sigma, we distribute them with frequency Q sigma. So we put 1 at places 1 over Q1, 2 over Q1, etc. And do the same thing for 2. And then we collect those one by one from left to right. In case there are 2 symbols located at the same place, we just collect them at arbitrary order. And we do so until reaching the time n. And that's our construction for S. But because of the time limit, please look at our full paper to see why this S works. But this is a very simple argument. Moving on to the next, we are going to show quantum security of a Spreakeasy random function. But what is a Spreakeasy random function? It is a function with many keys and the input, such that for every key ki, it is a pseudo-random function, subject to some minor technical constraint. And we care about this Spreakeasy random function because it gives rise to a KEM combiner, which combines multiple KEMs into one that is secure as long as at least one of the component KEM is secure. An efficient hash-based instantiation by Gaikon, Huru, and Petrin is already proven classically secure, but quantum security is previously unknown. And as our compiler, as our main application of compiler, we show quantum security of this instantiation. The proving strategy is sort of a hybrid argument where we start with an initial querying pattern involving the oracles H prime, an auxiliary oracle H prime, and also evaluation oracle F. And from left to right, we replace every H prime to H and every F to R, where R is a random function. Let's look at the loss for replacing H prime to H. Oh, for replacing a block of H prime to H, the security loss is kind of proportional to the block size, QHI. And summing up those, we get a security loss presented here. Without any compilation, the best we can say is the block size is no bigger than QH, but there are roughly QF such blocks. So we are having a QF linear blow up on the security loss. With naive compiler, as mentioned earlier, we are having the sum of the block size no bigger than QH plus QF, and the same sort of blow up on QF. In typical cases, QH is a lot bigger than QF, so this is actually also an unwanted blow up on the security loss. Finally, if we use our compiler, then we can say that the sum of the block size is no bigger than 2 times QH. Likewise, we only have a factor 2 blow up on QF. This gives only a constant blow up on the security loss. And so indeed, our proof crucially relies on the compiler. Finally, let's give a brief summary. Our results consist of 2 parts. In the first part, we give a generic compiler transforming any adaptive algorithm to a static one with only like n times blow up on each respective queries. And this allows us to simplify existing results, but also obtaining enhanced bounds. In the second part, we give the quantum security of the hash-based Spreakeasy random function And consequently, the resulting term combiner using this F, this split-key random function is content secure. The takeaway is, if for the future you are dealing with adaptive adversary, just use our compiler to make your life easier. That's it. Please look at our full paper for more detail.
So we have time for probably 2 questions.
Do you have any like a lower bound for the number of queries you need in the compiler? Like, is your compiler optimal or how far from it?
Okay. So the question is about optimality of our compiler. That's a good question. Indeed, it's not optimal because one can always sort of removing one symbol, one less symbol from the compile string. But we also expect this compiler to be rather optimal, whatever that means. But also, like, we don't have a lower bound, so that would be an open problem.
So maybe I'll ask a question. Is it meaningful to consider quantum algorithms where they like query multiple oracles in superpositions? They maybe have an index that, like a quantum index, right? That controlled on which they query a particular oracle. Like, is that something that is meaningful to consider? And do you think your results might extend to that setting?
Yeah, we also think about this question earlier. But sort of one immediate question we encounter is that we cannot even define what's the query complexity for each individual oracle, because now we sort of pair different oracle with different number of queries. Yeah, so if you query this oracle, but then with the second oracle in superposition, then it will be an immediate first question what we actually mean. So yeah.
All right, let's thank the speaker again. All right, so up next, we have Sungin Lee, who's going to tell us about the parallel reverse pebbling game, analyzing the post-quantum security of IMHFs.
All right, thanks for the introduction. I'm excited to tell you about the reversible pebbling game. This is a joint work with Jeremiah Blocky and Blake Coleman. So in this talk, we'll be going to consider the problem of quantum pre-image attacks. So in this attack, we are given a function f and a target output y, and we want to find an input x such that y is equal to fx. And we're going to consider the setting where we only have a black box access to the function f. So classically, we need only 2 to the n, we need at least 2 to the n black box queries to the function f to solve this problem. But in quantum computing, we have a famous algorithm called the Grover's algorithm, which only requires at most 2 to the n/2 black box queries to the function f, which is a substantial speed up. And actually, this is tight. So we want to characterize the full cost of a quantum pre-image attack. So I mean by the full cost, it is defined as the space-time cost of a quantum circuit C that finds the pre-image of the function f. So this is defined as the width of the circuit multiplied by the depth of the circuit. So given a full like a Grover circuit, we take as input the quantum circuit CF, which evaluates the function f. And then it calls the function sequentially roughly 2 to the n over 2 times. So the full space-time cost of the attack is going to be W times D times 2 to the n over 2. So we can ask a natural question. So how do we characterize the space-time cost of a quantum pre-image attack? And to do so, we need to find the space-time cost of a quantum circuit CF. So the next question is, can we build the function f with high space-time cost to resist quantum pre-image attacks? A natural candidate here is something called the memory head functions, which is used in password hashing. So basically, memory head function is a function that requires a large amount of space to compute. And here we will consider the special type of memory head functions called the data independent memory head functions, which is useful in because it is resistant to side channel attacks. So a memory head function is defined by graph G, which encodes data dependencies, and a hash function H, which is usually modeled as a random oracle. And the function is computed by evaluating labels, where each node here is telling you the intermediate data labels, which is produced during the computation. So classically, to evaluate an IMHF, we oftentimes use the language of the black bubbling game. We have 2 simple rules. We want to place a node at the end of the target node, and then we can only place a new pebble if all of the parents are previously pebbled. So for example, we can start placing a pebble on node 1 and node 2. And now we have all the dependent data values to evaluate node 3. So we can place a pebble on node 3. And we can just discard a pebble from node 1 to free up space. And then finally, we can place a pebble on node 4. And we can discard pebbles from node 2 and 3 to save space. So the space-time complexity is defined similarly. So for above example, we never used more than 2 pebbles during the computation. We have total 4 pebbling rounds. So the space-time cost is 4 times 2, which is 8. So back to our first question, we can ask, so we have a black pebbling game. This is a useful metric. So can we use this black pebbling to analyze the space-time cost of a quantum circuit? So unfortunately, the answer is not so simple. And the reason is that the quantum circuits must be reversible. But considering this particular transition from 2-3 to 4, this is not a reversible transition because deleting things in the quantum random oracle model is not that simple. So we can delete things in the quantum random oracle model by using on computation like this. So this is a useful tool, but one thing to keep in mind is that to remove a pebble from node 3 using on computation, we need to have the parents of the node in memory. So, so the prior work introduced a sequential reversible computation and reversible pebbling game to remedy this issue. And they analyzed the space-time trade-offs in quantum computing. So one might wonder, can we just use this sequential reversible pebbling game to characterize the space-time cost of our quantum attack? But unfortunately, the answer is still not suitable due to the word sequential, because the circuit can evaluate the hash function H in parallel. So for example, we have this graph, and this is our sequential pebbling. And we can notice that the number of steps is linear to the size of this graph. So the space-time cost is relatively high. But in the parallel pebbling, we can finish by really a short step, only using log n steps. So the space-time cost can be decreased because the time cost is decreased from n to log n. So coming back to our first question, how to characterize the space-time cost of a quantum pre-image attack against the IMHFs. And we give the partial answer by introducing the parallel reversible pebbling game and by studying some attacks against IMHFs in this pebbling model. So a parallel reversible pebbling is very similar to a classical pebbling with 2 additional rules. The first rule is pebble can be deleted only if all of its parents were previously pebbled. And then if a pebble was used to generate the new pebbles, we have to keep the pebble. So this second rule is to ensure that the circuit is actually reversible. So we want to compare between the classical and reversible pebbling. So here's an example of a classical pebbling. This is a legal classical pebbling, but if you look at carefully, there are a number of rounds which violated our reversible pebbling rules. For example, nodes in the red boxes, this is illegal in a reversible pebbling because we cannot remove pebbles while its parents were not all pebbled. And these nodes in the blue box, they're illegal in a reversible pebbling because they were actively used to place a new pebble on node 3 and 5 respectively. So this is our reversible pebbling. So we can observe that we need to actually keep those extra pebbles in round. So we study several reversible pebbling attacks. The first attack is on a line graph. And one reason why we care about the line graph is because we have several widely deployed hash functions, which can be characterized as a line graph. So we can ask if a line graph is resistant to quantum preimage attacks. Classically, this is trivial because we have a really simple pebbling, which has space-time cost only n. So it's not resistant. But when it comes to quantum computing, it is not very trivial. Because we cannot delete just pebbles wherever we want. So we can come up with a naive reversible pebbling, which is just walk a pebble and no deletion, which has space-time cost n square. But it is not trivial if we can come up with much better attack. So here we give our parallel reversible pebbling, which has a space-time cost a little slightly larger than n. And then we note that we modified the prior work, but we just formalize it in the language of our pebbling. And this is the second attack. And actually, due to the time limit, I will just skip this attack, and I will just revisit later with our result. And I will just focus on our last attack, which is using an induced line graph. So given a graph G, we can split into blocks of size B. And we can create a line graph of a size n over b. And then after we find our pebbling on a line graph, we can transform the reversible pebbling of the line graph back to the original graph G. To do so, we need to define one notion, which is called a skip node. So here, the red node above is called a skip node because the red edge skips over the next block. And the key intuition of our attack is if we keep those skip nodes around, then we can easily transform a reversible pebbling of the line graph back to our graph G. So for example, consider this following reversible pebbling transition. So suppose that we have a pebble on this node, then this corresponds to having pebbles in the block above. And this is a legal reversible pebbling transition. And to do so, we want to place the pebbles on the block above, but which is impossible because of this red edge. So we actually need to keep a pebble on the skip node to place a pebble here. Then we can pebble like this block. And this property also holds when we delete a pebble from the graph. We want to delete pebbles from the block above, but to delete this pebble from this node, we actually need to keep a node on the skip node. So this is an example. So given a graph G, we can make a line graph, and then we can transform our reversible pebbling to the original graph. So we can prove that the space-time cost of our original graph G is S times n plus B squared times the space-time cost of the line graph, where S is the number of skip nodes and B is the block size. So we consider an IMH candidate called DR sample, which classically is known to have stronger memory hardness than argon 2I. So for DR sample, we show that the space-time cost of a DR sample is as follows. And there's one thing to note. DR sample actually has a more efficient reversible pebbling attack than another IMHF candidate called argon 2I. But we only show the upper bound, and we didn't show our lower bound. So it is an open question if which one truly has a higher space-time complexity. And so far, we only considered inverting a function f on a single target output y. But we can consider the same problem with inverting a function on multiple target outputs. Then the attacker can amortize the space-time complexity using over running Grover in parallel. So we introduced the notion of amortized space-time complexity for parallel reversal pebblings, and then we give some result by extending a non-reversible attack of Owen and Blocky, and we have the much efficient attack than a naive pebbling for Aragon 2i. So there's a conclusion, and we have several open questions, but due to the time limit, I'll just mention the last one. So here we only give the upper bound of our attack, so upper bound of the space-time cost. So we are interested in come up with a lower bound of a space-time cost as well. And then if we have a lower bound, can we come up with a reversible pebbling reduction so that the lower bounds carries over in the parallel quantum random Oracle model? All right. Thank you. And I'm happy to take questions.
So I think we have time for one question from the audience.
So just to make sure, so your paper is an attack paper, right? You introduce the notion of pebbling such that when you understand this notion of pebbling for a particular construction, it gives you an attack, but it doesn't give you a security proof.
Right, exactly.
And maybe like a very quick follow-up. And so what's your kind of TLDR? Do we have something where you can probably like one of the functions which probably has a good resistance to quantum parallel attacks? Do we have any positive results? Like this is a function to use?
So we haven't, can you repeat the question?
Well, essentially, so you have some attacks which kind of shapes like small factors. Do you have something where you will actually recommend, okay, this is a function that I recommend to use because we actually have a proof of security, which is the best possible or something?
No, we haven't proved it. Yeah.
Would you conjecture that your model accurately captures quantum complexity, or do you think that there might be a better model out there?
No, we haven't.
No idea.
Yeah.
All right, let's thank the speaker again. All right, so next up, Nick Spooner will tell us about quantum rewinding for many round protocols.
Thanks, Femi. Yeah, so this is joint work with Russell Lai and Julia Malavolta. Apparently, this is a PowerPoint running in Keynote, so if anything goes really wrong, that is why. Okay, so
this paper is about a particular sort of family of many round protocols, which are informally called lattice bulletproofs. So this was introduced only by Lubashevsky, Nguyen, and Zeiler, and then sort of variants of this protocol appeared in Albrecht and Lai and Atimer, Kramer, and Cole. And it's all sort of a similar concept. So you have some wide matrix A, which is a random matrix drawn from the H by N matrices of the ring. So think about H as being the security parameter and N being some largish thing. And what you want is a succinct proof of knowledge of an SIS preimage, short integer solution preimage. So this is like a short X such that Y is equal to A times X, where short by short, I mean sort of in the infinity norm over this ring, but don't worry too much about that. So the proof goes as follows. This is the proof of knowledge. So what the verifier is going to do, he's going to choose a challenge, a random challenge, which he's the prover, and this induces this sort of folding of this matrix A. Okay, so we're gonna split matrix A up into two halves, and we fold it sort of over the challenge alpha. So we see a combination of the left half of the matrix plus alpha to the right of the matrix gives you a mix which has the same height but is half the width. Okay? And having the preimage X is going to do the same thing to X. Okay? So he's going to fold X, but notice that he's folding now with alpha on the left half. And nothing on the right half, and this gives him a vector of length n half. And then what happens here is that so if you look at like A prime times X prime, this is a quadratic equation in alpha, and notice that like the way that we sort of set things up, the original Y, so A times X, appears as the first term in this. So so there's this like linear term, alpha times Y. And then we have some cross terms, so some junk. And so what we're going to need to do, basically, we want to reduce to checking this equation, and so the prover is going to have to send these cross terms. And I apologize, I've made a mistake here. So these cross terms should actually be in the first message. This is a 3-message protocol. So ALXR and ARXL are things that the prover sends at the beginning before he sees alpha, and then the final message of this protocol is X prime. So the verifier can then, like, given this information, he can check this equation at the end, and in this way he's convinced of the existence of this preimage with only like n half communication. Okay? So we've like saved a lot of communication, right? The original image is n ring elements, and now we're only using like roughly n half ring elements. Now, you know, n half is, I said succinct, n half is not really succinct, but what you can do is notice that this A prime X prime equals Y prime is itself instance of this cis preimage problem, right, for X prime. And so we can just recurse. So rather than doing this X prime, which is large, we just we prove the existence of X prime. Okay? We do this log many times, and so the total communication is order log n. So what do we do in this paper? Basically, we prove that this proof system with like this recursive log many counts is a post-quantum proof of knowledge of a cis preimage, assuming quantum hardness of RWE. So, you know, you might be wondering, well, actually, I guess with Ethan's talk, you're probably not wondering why this wasn't known before. Basically, it's because the classical reduction, the original reduction is only for classical adversaries. It's a classical reduction to LWE, right? But it doesn't work for quantum adversaries. And so the way that we prove this result is in 3 steps. So we come up with these new soundness notions for multi-round protocols, which I'll get to a little bit. So recursive special soundness and last round collapsing. Recursive special soundness is kind of a more refined notion of tree special soundness, if you've seen that before. And last round collapsing is an adaptation of the collapsing property to multi-round protocols. And we give a novel rewinding algorithm for any protocol that satisfies both properties. Finally, we show that the lattice bulletproofs sort of family of protocols satisfy both properties, assuming QLW, the quantum hardness of LWE. So let's get into a little bit.
So I want to just like take a quick look at the classical proof that this protocol is secure. And it is basically tree special sounds. Okay, so what I do is I kind of start from my original. This should be, sorry, LNR should be at the top here as well. So let's just think about the 3-message protocol, right? So I imagine running the prover on the 3-message protocol for like a challenge alpha 1, and I get out some x prime 1, right? And then I do the same thing for alpha 2, and I get some x prime 2, and I do the thing for alpha 3, and I get some x prime 3. Here, like these LNRs, these should be all the same LR, and they should be at the top. Okay, so so then I get these sort of three preimages, x prime 1, x prime 2, x prime 3. With the second message in the 3-message protocol, and I can combine them together in some way, basically by solving a linear equation. So long as alpha 1, alpha 2, and alpha 3 are all different, and all of the and the verifier accepts all of these transcripts, I can combine them to get back an X that is a solution to a short solution to the original equation. Now, of course, whoops, sorry. Now, of course, we're not using this 3-message protocol, but we're using the recursive version, so with log many rounds. So what we do is we say, well, okay, the prover is not going to give us x prime 1, x prime 2, x prime 3 in the clear. He's going to prove to us that they exist, and so we're going to run the extractor in order to get these, and we do so recursively. So we just in the end we end up with a complete ternary tree of accepting transcripts, and from that we can extract an X. This is why it's called tree special soundness. Okay, so how do we get this tree? It's sort of by a kind of simple depth first search algorithm. So I'm going to sort of just write it down. Imagine that we're at some point in the tree, like indexed by a list of challenges alpha 1 up to alpha I minus 1. And we want to extract these 3 challenges here: alpha 1, alpha 1I, alpha 2I, alpha 3. So what we do is we just kind of recursively explore the prover tree. So this p tilde is our malicious prover, and so we obtain the LNR, the junk terms from the malicious prover, and then we're going to recurse down the tree, and we're going to ask the tree extractor to produce the preimage xi1 that we need for the ith level of the tree. And if this fails, then we're going to output fail. And otherwise, we're going to repeat this star step until we get 2 more successes. So we're going to get three different choices of xi. And then I'm going to return this xi minus 1, which is some combination of LNR and all of these xis. Okay? So this is like the sort of atomic step, if you like. So this is like just some depth first exploration of the tree, basically. Okay, yeah, this is a keynote. So this is some depth first exploration of the tree, and so there should be a base case of what happens at the leaves of the tree, and what happens at the leaves of the tree is we get actually like an actual preimage for the hash function of that leaf. Which is this x prime, and basically what I do is if this thing is an exception transcript, so like if everything was correct all the way down to the bottom, then I'm going to return x prime LR, otherwise I output fail. So this is where the fail comes from. Basically, the prover can just like not succeed in convincing me on some sequence of challenges, and so I should output fail here. Okay, so quick analysis of this. So let's say that the probability that the malicious prover wins is mu. And so I can define like the residual probability at any node as the probability over continuations from that node of the probability that the prover wins. And so you can see like it's not too hard to show recursively the probability that you fail. So like the ti plus 1 outputs fail, right? Is just the probability that is just like mu like for that particular node. And so the overall probability that you succeed in extracting is mu, which is great because that's the probability that the prover does anything interesting at all. And the expected running time is a little more interesting. So this is where we use this fact that you have this like early termination. So basically if ti plus 1 outputs fail the first time, then you just give up, right? And so you always run Ti plus 1 once, and then with probability mu of this node, you run it 2 over mu times to get 2 more successes. And so the overall expected running time is 3 times the time for the next for Ti plus 1. And so if you solve the recursion, then the time for T1 for actually extracting the thing is just poly lambda times like 3 to the log n, which is poly lambda. Great. Okay, so why does this fail in the quantum setting? Well, it's because of this repeating star until 2 more success. We all know that quantum, hopefully by now, we all know that quantum rewinding is really hard. And so, so like this repetition is what causes the problem. But by now we know how to do quantum rewinding, right? We have some powerful techniques. This should be CCLY22. So the question, why aren't we already done? And you could say, well, why don't I just like apply my quantum rewinding techniques in place of this like repetition? And the problem is basically that known quantum rewinding techniques require this Ti plus 1 to be projective. This is kind of a technical quantum-y condition. And usually this is achieved by running Ti plus 1 in a unitary fashion, also technical quantum-y condition. The upshot of this is that this doesn't really play well with like expected polynomial time extraction. And so because basically if you run something in a unitary fashion, you need to know how long you're going to run it for. It is like not possible to run something in a unitary fashion if you don't know it's an a priori bound on its running time. Okay? And so this causes a huge headache. The way to fix it is basically by going to the classical extraction. I don't really have time to go over this, but to go back to the classical extractor and like make it work in fixed polynomial time. The idea is basically you want to just kind of predict when the extractor is going to succeed. So you're going to like try and like before you recurse, you're going to try and figure out if the extractor is going to succeed already and therefore not waste time. I'm happy to discuss that offline if anyone wants to know about. And so okay, yeah. So basically, we use the CMSE measure and repair technique to achieve this in the quantum setting. So what you do is you just perform a measurement of whether the like using sort of quantum probability estimation type techniques, you perform a measurement of whether the thing is going to accept, whether the prover is going to convince you on some particular transcript. Sorry. With reasonably high probability, some particular prefix with reasonably high probability. And if yes, then I'm gonna like continue the extraction, otherwise I'm not going to do it. And then I'm use this repair technique to basically repair the residual probability after doing this measurement. So the proof idea is basically this second step here is kind of this step with star is computationally indistinguishable from the first step. And so like it's like I'm doing the same thing twice, and because things are projective, it looks like I didn't do anything at all, and I can kind of remove it, and then an appeal to the measure and repair analysis from CMSE. Okay, so it was very quick, but I hope that it was somewhat illuminating. This is sort of where we use the Lagrange collapsing. Sorry, so if you want to get this xi, you actually need it to be you need some collapsing property on it. Okay, so that is all. Thank you very much.
So we have time for maybe one very quick question.
So it is. Oh yeah, sorry. So the question was, is there any slackness in the solution? So these lattice bulletproof protocols, these kinds of lattice-based proofs of knowledge, they exhibit a property where the solution you extract is like worse than the one you would get if you were the honest prover to begin with. So this is also the case here, but it's not made any worse by the quantum analysis. Like it's just a property of the classical analysis. Yeah.
All right, let's thank the speaker again.
Thank you.
So we'll have a break now, and I think we're back here in 30 minutes.